Hello guys, in this video lecture I'll be solving some rotational kinematic problems which are also solved in my example problems, which are already posted on my courses. So first, to get started, first let me quickly show you all the equations we're going to need actually to solve rotational kinematics. So it's basically we are comparing rotational variables with the translational linear motion variables. So for example, let's get started. So we had kinematic equations, right, with constant acceleration, final velocity, initial velocity plus at. Now this will translate into in rotational motion. This final velocity will be final angular velocity, initial angular velocity omega, plus a will be replaced by alpha, which is the angular acceleration, and time is same. So next is uh, the final position, initial position plus initial velocity time plus 1/2 at square, right? And that will be translated into, so the linear position x will be uh, replaced by the angular position theta f. Okay, theta initial plus initial angular velocity t plus 1/2 a will be replaced by alpha t square. So one more. So final velocity square is initial velocity square plus 2a x minus x final minus, so that you can also call delta x, will be translated into so final velocity is final angular velocity omega square, omega initial square plus 2 alpha, and this will be theta final minus theta initial. So, and that's the total angular displacement. So these are some uh, kinematic equations in translational motion, linear motion, and in rotational motion. So we'll be using all these formulas to solve some kinematic equations. But however, be careful that these formulas are only for a or alpha constants. You can use this formula only if the acceleration is constant. If acceleration is not constant, then you'll have to do calculus. You'll have to use the calculus, which I'll show you more examples. Okay guys, so let's get started. So the first problem, just to get started, first problem is like something like that. A wheel initially rotates at 20 radians per second and decelerate, right, at a rate of 10 this. So how long does it take to come to rest, and so on. So let's first solve the first problem. It says a wheel is initially rotating at 20, initial angular velocity is 20 radians per second, right? And it says it's slowing down, it's slowing down. So that means alpha is 10 radians per second square, but since it is slowing down, deceleration negative. So it says how long does it take to come to rest. So since it comes to rest finally, right, so omega final is 0. So then use one of the kinematics, right? So it's alpha is constant, so you can use one of the kinematic equation in rotational form. So the good formula is obviously, right, this simple one. So this is 0, this is 20, plus alpha is negative 10, and time t, so t is 2 seconds. So it comes to rest within 2 seconds. So next question is what is the total angle it rotates. So first you have to find out what's the total angle delta theta or theta final, right? And then total number of rotations is just delta theta or theta final divided by 2 pi. So that's what we will do, because one revolution or one rotation has 2 pi radians. That's the key point. Okay, so first let's figure out the total angular displacement in 2 seconds. So then you will have to use one of the formula, right? Since you have alpha, you have everything. So theta final is theta initial plus initial time plus 1/2 alpha t, one of the kinematic equation, right? So theta, we're finding theta final. So theta initial, let's say, is 0. You started off from 0 angle, and omega initial is 20 revolutions, radians per second. Time is 2 seconds because we're calculating the total angle it rotates within 2 seconds, plus 1/2 alpha is, don't forget the negative sign. So theta final 40, so minus 25 20, so 20 radians. So the total number of revolution it made before it comes to rest is then the total angular displacement it made in 2 seconds divided by 2 pi angle. So 20 divided by 2 pi, that's the total number of revolutions it will make within 2 seconds when it comes to rest. Alright, so that's, so let's continue. So the next problem I like to show you is this. So for example, if so you're given some variable theta angular displacement in terms of t. So here theta is not, theta is changing as a function of time like this, right? So, and first question is, what is the angular velocity at t is 1.2 seconds, and what is the angular acceleration as a function of time? So first question is, you're given the angular position as a function of time, 0.1. So I'm just not going to write down all the units. So it's t squared plus 0.6 t. So first question is, what's the angular velocity, right, at t is 1.2 seconds. So, and you just need to use the calculus, just derivative, right? So angular velocity is just d theta over dt, right? So then this is just the derivative of this. So d over dt of this function is pretty easy. So 0.2 plus 0.6, yeah, the t, right? Okay, now put t as 1.2 because we're finding the angular velocity at 1.2 seconds. 1.2 seconds plus 0.6. So 0.84 radians per second at 1.2 seconds. So that should be the answer for this, right? And next, what is the angular acceleration as a function of time? So alpha. So then you do one more derivative, d omega over dt is alpha. So angular acceleration is the time derivative of, you know, the angular velocity. And here we know, so omega as a function of time is this. So just take the derivative of this, time derivative of that, 0.2 t plus 0.6, and if you take the derivative of that, 0.2, just 0.2. So alpha is, and its unit should be, so you can clearly see alpha is constant, right? It came out alpha, the angular acceleration in this problem, constant because it doesn't depend on time. All right, let's move on. All right, so the next problem I'll be solving is something like this. Wheel is spinning at 21 radians per second, but it's slowing down with an angular acceleration given by 3t squared. It's alpha is 3t squared magnitude. At what time will it stop? So So here's how you do. So this is the wheel. It's rotating, spinning counterclockwise at initial speed is 21.0 radians per second, and alpha is given by 3 t square magnitude, right? But since it's a deceleration, right, is negative, and it's acting at what time will it stop, right? So we need to figure out at what time omega final is equal to 0, right? That's the question. But since alpha is not constant, it's time dependent. So you'll have to use calculus to find omega. So remember, alpha is d omega over dt, so d omega is alpha dt. So you just need to integrate that. After setting this up, you just need to integrate from some initial angular velocity to final angular velocity, which is 0. And here you're integrating from some 0 to some unknown time, and we are solving t. So d omega, so integration of d omega is omega itself, and your limit of integration is omega. Initially it is rotating at 21 radians per second, final angular velocity is 0, and here you are just integrating this alpha function, so which is negative 3 t square 0 to t. So this will give you negative 21, 0 minus 21, negative 21, negative, so this is going to be 6t, but put the limits 0 to t is going to be negative 6t. So t is then 21 over 6. I'm sorry, I made a mistake here. I'm integrating, so 3 t square t cube over 3. Okay, I made a mistake here. I was doing derivative. So the integration of t square is t cube over 3, and then you put the limits. So let me do that. Negative 3 will cancel out, right? So t cube, that's it. So t is then 21 cube root, and that's going to be 2.75 second. So that should be your answer. Okay, that's how you should solve. Okay, the next problem we're going to solve is, so let's continue. So something like that. At time t0, the current to a DC electric motor is reversed, resulting in angular displacement of the motor shaft given. So don't worry about this sentence actually. So you're given the angular position of some rotating wheel, something like that. So first question is, at what time is the angular speed of the motor momentarily 0, right? So you're given your theta angular position, theta function 35 t minus 1.5 tq, right? And then it's acting at what time the motor momentarily stop, right, becomes 0. So that means you need to find out the angular velocity, which is nothing d theta over dt. If you take the derivative of that, 35 minus 3 4.5 t square, right? So that's your omega. Omega function is given by this, and then you just set it to 0, because we are going to find at what time the angular velocity becomes 0. So at this time the angular velocity becomes, so 35 divided by 4.5 square root, and that's going to get you 2.78 second. That's pretty easy. So second part is now, what is the angular displacement in revolutions that the motor shaft turns through between the time the current is reversed and the time instant angular velocity is moving? So So during this time, 2.78, what's the total number of revolutions that this motor makes? So then you just need to find out the total angle, total angular displacement, right, within this time. In time is 2.78 and divide by 2 pi, and that's going to give you the total angular total number of revolutions. That's the main idea. Okay, so then we know the theta function. So theta function is given by 35t. That's the given theta function, but at t is 2.78 when the motor shaft, motor just momentarily stops. So then theta, we can call theta final is 35. So put the numbers 1.5, 2.78 cube. So that's gonna give you 65 radians if you do this. And the total number of revolutions it made during this time is just need to divide by 2 pi, right? So 265 by 2 pi gives you 10.4 revolutions. So it made about 10 revolutions within this 2.78 seconds. All right, so I'm going to show you one more problem, which is something like that. The angular velocity as a function of time of a particular point on a rotating wheel is given by this equation. That's the angular velocity as a function of time. The point is located at angular position plus 2.09 radians at t0. So calculate the angular position as a function of time. So you're given the angular velocity as a function of time. So I'm just gonna write down the magnitudes, right? And it says theta initial is 2.09 at initial time 0 second, right? And it's asking what's the angular position as a function of time. So it's asking is the general angular position theta as a function of time. So you're given the omega, so it's asking you to find the theta. So and then to do that, first show this relation. Since omega is d theta over dt, right? So d theta will be omega dt, right? Now you have to do integration. So integration from some initial angle to final angle theta, that's what we are finding. And here you're integrating from some initial time, which is 0 to t. That's it. So this d theta is the integration of d theta is theta, but put the limits. So initial theta is 2.09 to some angle, right? That's what we are solving for. Is omega function is function is given to us, and then you're integrating. So this is going to be theta minus 2.09 radians, and the integration of this is 3t cube over 3. Make sure to put the limits, plus 2t square over 2. Again, put the limits, right? And that's it. So theta 2.09 is, so this t cube, again this is t square. So theta as a function of time is t cube plus t square plus 2.09 radians. Alright guys, so these are some rotational kinematics with alpha constant or non-constant examples. So you should be good to solve some of the assignment problems, which is due Monday.